So here, back to our equation. So we have this equation. And so what I had originally set up was we have the gravitational constant, which actually never changes. So we're going to multiply each one of these by a factor that tells us how much of it there is, okay? So the constant is never gonna change. So this one's always gonna have a 1 in front of it for this exercise, okay? We have the mass of the second object. Whatever it is, it doesn't matter. So variables are like a container. It's like we put them in the box and it's in there. Okay, whatever that mass is. Okay, same with mass 2. It's like a little box and we put a mass inside. And now what we're going to do is we're going to start multiplying the amount of mass and we're going to see what the resulting force does. So right now we have one of those masses and we have one of those masses and we have our base distance. So let's go to the gizmo and let's set this up. So let's go to a distance of, let's keep it at a distance of 10. So that's going to be our base distance. And let's set our masses to 1 each. Okay. So our force is 0.0067. So I'm going to write that down so that we don't forget. So our force is 0.0067 newtons. Okay. So now what I'm going to do is I'm going to go back to our numbers here. And I'm going to, if I multiply all those, our base force is multiplied by a factor of 1. So our base force in this case is 0.0067 newtons. Okay. So now I'm going to double the first mass. Okay. I'm going to double the first mass. So multiply that times 2. So 2 times 1.0 is 2. And notice what happens to the mass. I mean, the force. The force is actually double what it was. So let's go and take a look. If we took out all the variables, we could multiply these factors in front together and find out what our force factor is. So 1 times 2 times 1 is 2. Divided by 1 squared is 1. So our force is going to double. Well, let's go check it. So what's double of 0.0067? If I double that, now why is it rounded like this and a little bit different? Because there's probably a lot more decimals in the calculator in the computer, okay? But that's double what we had before. All I did was double the mass and I doubled the force. What if double the other mass? 1 times 2 is 2, times 2 is 4. Divided by 1 squared is still 4. So that's going to equal 4 divided by 1. 2 times 1 is 2. 2 times 2 is 4. Divided by 1 squared is going to be equal to 4. Okay, so our force should multiply times a factor of 4 from what it was originally. So let's go to the gizmo and check it. I multiply that one times 2, I multiply that one times 2, and our force is now 2.0267. So originally we had 0.0067, multiply it times a factor of 4, 0.0268. So what I want to show you is, so this, what I'm showing you is working, okay? Because here's what the test question is going to say. The test question is going to say, you have a force of gravity that equals 10 newtons, and you double one of the masses. What's going to happen to the force? So if I double one of the masses, I'm going to multiply my force times 2. So a simple way to look at this is you get rid of the extra variables because it can be confusing. And now we just do this. 1 times 2 times 1 is 2. Divided by 1 squared is still 2. Okay? If I double both masses, 2 times 2 is 4. Divided by 1 squared is 4. Okay? Well, let's say I quadruple one and I triple the other one. 3 times 4 is 12. So the force is going to be 12 times as big. So that seems pretty simple, okay? But you got to be careful. You got to make sure you read carefully. Does it say it doubles one mass or does it double both masses? Because that and that are two different things. If we cut something in half, 1 times a half times 1 divided by 1 is still going to be a half, but in physics, we don't like to leave it as a fraction, so it's going to be 0.5 times the force, okay? But you just keep doing the same thing, okay? All right, now the tricky part is when we start changing the distance. So let's go and let's take a look at the distance here. So the first, we're gonna double the distance between them. We're not gonna change the masses, we're only going to change the distance. So let's go back and let's reset our masses, okay? And this time, we have our base force of 0.0067 newtons, but this time we're gonna go from 10 meters and we're gonna change it to 20. So let's do that. I'm gonna grab one of these and I'm gonna drag it out to, doesn't matter which one you move, but I'm gonna drag it out to 20. And we've got this new force. So let's go and check if my method of math works out for us, okay? So I've doubled the distance, but 2 squared is equal to 4. 1 times 1 times 1 is still 1, divided by 2 squared is 4. So now our force is multiplied times 1/4. Okay, so 1/4 times F. So let's go back to our gizmo, and we said 0.0067 times a fourth. Well, that's the same as dividing by 4, right? 7, which rounds to 0.0017. So we've actually, when we double the distance, the force gets smaller by 1/4. The force gets smaller by 1/4, okay? If we go farther apart, the force of gravity gets weaker. We go farther apart, the force of gravity gets smaller or weaker, okay? All right, so let's try another one. Actually, first, let me go back. So once again, we can now start doing this. We can just get rid of these variables. We got to know that they're still there, okay? But it just makes it easier to see. So that's what I just did, okay? 1 times 1 times 1 divided by 2 squared. Okay, so now let's triple the distance. Let's triple the distance. What's 3 squared? 3 squared is 9. So that means this is going to become 1/9. Well, let's check it. 1/9 of our original force. So our distance is 20. Now we're going to make it 30. Let's go to 30. 30 meters, and our force is 0.0007. And this time I am going to use a calculator. So let's clear. And let's do 0.0067 times 1/9. And we get this exponent, okay, which is, so 10 to the negative 4th means we're dividing 7.4. And so we're going to go 1, 2, 3, 4, and then put zeros in front of that. So 0.007. And that's what you have right here. Bottom line, though, is we triple the distance, the force gets smaller by 1/9. Now let's switch it up on us. Let's try something a little different. What if I bring them closer together? Let's start at 10. So the force is back to our starting point. And let's do it by a half. Let's cut it in half. So we're going to go to 5 meters. Okay, at 5 meters, the force is this. So let's go check our math here. So we cut the distance in half, but that's half squared. So a half squared is going to be equal to 1/4. But we are dividing by a fraction. So if I get rid of these, it will make more sense. Okay. We are dividing by a fraction. And when you divide by a fraction, you got to multiply times the reciprocal. Okay. So 1 divided by 1/4 is equal to 1 times 4/1. So this is going to increase by a factor of 4. So let's go check it. Did this multiply times a factor of 4? So we have our 0.0067 times 4. 0.0268, is that what we have? 0.0268. So, but it's the same, okay? So this math method that I'm showing you can work without having to plug in all the 10 to the seconds, 10 to the 23rds, and all that kind of stuff, okay? So on your test, you might, or on your homework, you might be asked, if I cut the distance by a third, like I originally said, 1/3 squared is 1/9, because 1 squared is 1 and 3 squared is 9. So 1 divided by 9, because you have to square the top and the bottom when you square the whole thing, okay? But that means this becomes multiplied times 9. So you flip the fraction. So whatever you wind up here, you're going to flip it, and that's what goes in front, 9. Last thing that we need to talk about with this is basically the fact that in this image, the earth and the bowling ball are pulling with the same force. So the earth is holding the bowling ball, but the bowling ball is also holding the earth.